Well, let's get started. I suspect we're probably about it. I don't need to introduce Eleanor and James, but thank you very much for taking over our informal slot this week to give us a primer on Carroll gravity. I'll just go and close the door.
Thank you so much, Chris. Shall I start?
Yeah, go for it.
So, over the summer, Eleanor and I were talking a little bit about Carroll gravity. Carroll gravity is the ultra-relativistic limit of general relativity. So, in philosophy of physics, we spend a lot of time doing this and widening the light cones, good old Galilean space-time. But it's much less common to do this. Narrow the light cones and take the c to 0 limit of general relativity and see what pops out. So that's what we're going to be exploring today. This has been kicking around for a while, as we will explain and discuss. But for various reasons, physicists have become particularly interested in it in recent years. So just as a bit of background, the idea of Carroll gravity was first written down by Jean-Marc Lévy-Leblond in 1965. For those of you that don't know Lévy-Leblond, I'm just amazed by the number of philosophically interesting papers that he has. So if you're lacking for philosophy research projects, I strongly recommend to look at his output. In 1965, he wrote down Carroll gravity. Carroll does not refer to this guy. That would be weird, given his date of birth is 1 year. No strange retro-causality. In fact, it goes back to good old Dodgson, so named after Lewis Carroll. Why did Lévy-Leblond decide to name this theory after Lewis Carroll? Well, there are various reasons, various suggestive passages in Alice in Wonderland and Through the Looking Glass, the most obvious of which is the Red Queen's race. So this is where Alice tries to move but doesn't go anywhere. Here's the relevant passage. So, in our country, said Alice, still panting a little, you generally get to somewhere else if you run very fast for a long time, as we've been doing. A slow sort of country, said the Queen. Now here, you see, it takes all the running you can do to keep in the same place. If you want to get somewhere else, you must run at least as fast as that. So there's a sense in which nothing moves in Carroll gravity, hence this quote being, a reasonable thing to point to, and hence they're naming the theory as such. So we're going to go into the mathematical details of this a lot, but just to give you the idea, here's a relativistic space-time. We don't normally write out the inverse metric and the derivative operator, but compatible derivative operator, we can do that. Like I say, we can widen the light cones and go to Galilean space-time, which has everything that we know and love, like a standard of straightness, foliations of constant time, absolute time, a temporal metric, which you can split up in this way if you've got temporal orientability. If I do the opposite thing and narrow the light cones, I won't get a foliation, but I'll get a vibration given by the integral curves of this vector field Z if you are splitting up this upstairs object SAB in this way, again, assuming temporal orientability. We will explain all of this. So this is the kind of space-time structure which we're going to be looking at. Just to say a little bit about how this works in terms of group theory, if you take the Poincare group, and we all know that there are delicate issues here, but roughly if you take the c to the infinity limit, you'll get the Galilean group, which looks like this. And you'll notice that the temporal interval between two events is well defined here, but not the spatial interval. The opposite is in fact so if you take the c to 0 limit of the Poincare group. So the spatial interval between things is well defined, but the temporal interval is not. So stuff is flipped around in that way. And that invites interesting philosophical discussions already, which we'll get into, and yields different physics. Lévy-Leblond has a long passage about this, actually in French, and Jeremy told me off for including it untranslated in our original draft. So here's a translation, and here are the relevant bits of it. Just saying kind of what I've already told you. So two events separated by such an interval are obviously totally causally disconnected. When we can thus predict at the corresponding non-relativistic limit, the notion of causality will lose almost all content because the light cones have been narrowed to just being the integral curves of this vector field. The causal shadow of a given event is reduced to the very place where this event takes place. And as I said, in Galilean theory, the time interval between two events is an invariant. Conversely, here's the length of the spatial interval, which is invariant. So we want to explore all of this. Here's our plan. So that ends the cold open. Here's what we're going to say. So first we're going to say about the geometry of Carroll gravity, trying to follow roughly chapter 4 of Malamud, but the ultra-relativistic theory rather than the non-relativistic theory. We'll then explore how Carroll gravity is the ultra-relativistic limit of general relativity. We'll look at why people are interested in it and then engage in some philosophical discussions about its various interesting features, and then we'll flag some stuff to be done in the future.
Yeah, I think it's over to me.
Yeah, you can take the slides if you want.
Cool. Good. So, as always, we're doing space-time theories. We're going to start with the lovely four manifold. And a Carroll space-time looks like this. So we have our manifold. We have a downstairs degenerate spatial metric, which is going to give us a notion of spatial distance between any 2 points. And this has signature 0, 1, 1, 1. And then we have an upstairs temporal metric, which has signature 1, 0, 0, 0. And this is going to give us a notion of temporal distance between co-spatial points in our space-time. Good. And of course, they're going to be orthogonal, and they're also going to be compatible with our connection. Just like in the non-relativistic case, sorry. So just carry over the terminology there. You can kind of imagine this, right, by thinking about a non-relativistic space-time, and you replace all the downstairs indices objects with upstairs indices objects, and vice versa. Okay, good. And just to remind you how the signature condition works. So the idea is, if we have a degenerate metric, to make sense of the signature, well, we have a basis at each point, and then we just demand that if our vector is our one temporal vector, then it's going to annihilate that vector when we contract it with the spatial metric and give us 1 for any of our spatial vectors. And similarly for our temporal metric, right? So in exactly the opposite way, it's going to give us length 1 if we contract it with the spatial metric, and 0 for all the spatial vectors. Okay, good. So the next thing is that generically, we can always decompose our temporal metric at a point is a product of 2 vectors at that point. But there's no guarantee that that holds globally. When it does hold globally, then we can find a vector field which satisfies this for the whole space-time. And roughly, this vector field, the integral curves of that vector field, are going to provide us with a notion of co-spatiality between points in our space-time. Okay, good. And we all just assume this going forward. So our spacetimes, our Carroll spacetimes will look like this. And obviously, the compatibility and orthogonality conditions look like this rather now when we've assumed temporal orientability. It's worth kind of remarking on this condition because it's analogous in some interesting sense to the fact that the temporal metric in a non-relativistic spacetime is closed. We'll see this a bit when we talk about taking the ultra-relativistic limit. But basically, if you look at the compatibility conditions with the metric, so the covariant derivative of psi and the covariant derivative of h vanish, it obviously implies that the Lie derivative of h along psi vanishes. And yeah, this is interesting because it's a bit like, in some sense, to be explicated, the closure of the temporal metric in non-relativistic spacetimes. Okay, good. So I said that these objects function as temporal and spatial metrics. How do they do this? Well, first of all, they induce the classification of time-like and space-like vector fields. So a vector field is time-like if it has 0 spatial length, and it's space-like if it has some spatial length, as you would expect. Similarly, they also tell us about covector fields, whether they're space-like or time-like. So we can say that a covector field is space-like if the contraction with the temporal metric, our vector field psi, vanishes. Why is this a good thing to say? Well, because then if you integrate such a covector field along the curves of psi, which provide our notion of co-spatiality, you get 0, which is what you'd like. And time-like vector fields are all the other ones. The covector fields are all the other ones. Good. And sort of one important class of time-like covector fields are the unit time-like covector fields, right? Which contract with psi to give 1. Okay, good. So that's one way of classifying vector fields as time-like or space-like. We also have a different classification, which is equivalent to our first one, and has some sort of nice properties, so it's kind of worth remarking on. So first of all, you can show that a vector field is time-like if and only if it's a multiple of our temporal metric, so the vector field psi, for some scalar field, alpha, which is exactly what you expect. So the time-like vector fields are all and only the scalar multiples of our vector field psi. And similarly, the space-like covector fields are precisely the covector fields you get from lowering vector fields with our spatial metric. Right, okay. Good. Okay. So because the metrics are degenerate, they don't in general have a unique inverse, just like in the case of non-relativistic spacetimes. But as in non-relativistic spacetimes, you can specify an inverse relative to a choice of unit time-like covector field. So in the non-relativistic case, you'd pick your favorite unit time-like vector field and use this to define a projection onto the foliation, which is orthogonal to it. In this case, we're going to pick our favorite unit time-like covector field. This will also, providing that it's integrable, induce a foliation. And then we can define a metric by projecting everything onto that foliation. Okay, good. And so formally, those are the conditions which this metric, which we're calling h at hat AB, will satisfy in order to make it have those properties. Okay, and it exists and it's unique. So it has nice properties that you'd accept of a metric.
Sorry, can I ask a question
Yeah,
there? So in the lovely Misner, Thorne and Wheeler way of thinking about covectors, I'm supposed to think of these as really given by the level surfaces, which would, in this case, have dimension 1, so dimension 3.
Yeah.
And so this choice of a time-like covector field would be like a choice of a local simultaneity slicing, is that right?
Exactly, yeah. So it will give you a distribution of simultaneity slices. Of course, like that's not necessarily going to give you a local simultaneity slice because it might not be integrable. And it gives you simultaneity slices in the sense that they're not going to be like slices of your space-time which are oriented in the same way as the vector field psi, which is your time-like direction, right? Okay. Good. So one interesting feature, so our first interesting feature about the geometry of Carroll spacetimes is the following, which is that parallel transport of time-like vector fields in a Carroll spacetime is always path independent. Why is this the case? Well, here's a nice picture. So if you pick a time-like vector field at a point over here, and parallel transport it, well, we know that any time-like vector over here is going to be a scalar multiple of psi. So in order for it to be a time-like vector field over here, it's going to be a scalar multiple of psi here. So it must agree with psi up to some 6 scale factor, right? So providing we always have globally constant or locally constant scalar fields, we have a unique standard for parallel transport of time-like vector fields along arbitrary curves. And of course, constant scalar fields always exist locally. So we have this time-like path-independent parallel transport in Carroll spacetimes. Okay, good. The next interesting feature about the geometry of Carroll spacetimes is that just like in non-relativistic spacetimes, the connection isn't uniquely fixed by the compatibility conditions. So in non-relativistic spacetimes, this is the sort of content of Malamut proposition 4.1.5, 1.3, 4.1.3. Yes, it is. Which says roughly that you have a freedom up to a choice of 2 form field in your connection, which is compatible with the spatial and temporal metrics. In the case of Carroll spacetimes, it's fixed up to a choice of symmetric upstairs rank 2 tensor field. So that's another interesting difference between Carroll and Gaussian spacetime.
I'd only add that the fact that this is symmetric rather than anti-symmetric in the non-relativistic case means that it's slightly harder to deal with.
Yeah. So because it's anti-symmetric, right, then if it has nice properties, it could also be closed, in which case it's locally exact and you can use vector fields to get a handle on the properties of this anti-symmetric tensor field that you have in the non-relativistic case. Whereas because it's symmetric here, you can't do that. So it sort of makes interpreting what's going on with this a bit harder and a bit more involved. Okay, good. Properties of the Riemann tensor. I hope you all agree that it will satisfy these conditions. The compatibility conditions further imply that it has these two properties. So if we contract it in the second index with psi, it's going to vanish, right? Because just how the Riemann tensor is defined. This is the anti-symmetrized derivative of this vector field here, which of course, because the metric's compatible, the connection is compatible with the metrics, is going to vanish. And you get this condition in exactly the same way, just using the spatial metric. Okay, and you can then do a lot of index juggling and show that it satisfies these properties, which basically follow the standard arguments that you get. This one particularly is exactly the same argument for that property in the relativistic case, and the other two are fairly straightforward. Okay, good. So, as in sort of relativistic and non-relativistic spacetimes, obviously you can define the Ricci tensor by contracting these indices. You can also try to define a scalar curvature field if you like, but of course it vanishes, right? The easy way to see this is that because this object has got to vanish when you contract it with the second index with psi, of course this whole thing vanishes, right? Because you've just sort of switched over the order of which contractions you're doing when. Okay, and it's symmetric, as you would expect. There's an argument. I don't know if that's obvious or helpful, but it's not very difficult to show. It's about 3 lines of calculations. Okay, good. So we're now going to move on and talk a bit about some different curvature conditions you can impose on the Riemann tensor in Carroll spacetime. And the first curvature condition we're going to consider is the notion of spatial flatness. Okay, so of course flatness is the vanishing of the Riemann tensor at each point. We're going to say that a Carroll spacetime is spatially flat if all downstairs indices Riemann tensor, so you've lowered the top index with h, vanishes. Okay. So why is this a good definition? Well, it has the following nice property, which is that given any unit time-like covector field, T, and any space-like hypersurface relative to TA, so when we're defining space-like hypersurfaces relative to a unit time-like vector field, we're going to assume that the distribution that this unit time-like vector field induces is integrable. And so then we can integrate that and get a foliation. So if through any such space-like hypersurface, the downstairs index Riemann tensor vanishes throughout that space-like hypersurface, if and only if parallel transport of space-like covectors within this hypersurface it is at least locally path independent. Do you have a question?
So this is kind of a clarificatory question, but it's potentially a bit more. So it's fine if you want to. I don't know how open you are to interruptions.
I'm open to it.
I'm open to it.
So I mean, if you forget about the connection for a second and just think about the metric structure, you've got and compare it with Leibnizian spacetime, where you don't have any connection. It looks like you've just got these completely independent temporal one-dimensional spaces and then absolute distances between them. And so you've got a spatial metric on the space of these one-dimensional spaces. A three-dimensional, you know, the quotient of the four-dimensional space-time by the fibration. There's a natural notion of it being flat, just that three-dimensional quotient space being flat. But so I'm just interested in how that notion, which is very natural, just thinking about the metric structure independently of a connection, connects to this much more complicated thing where you've imposed these conditions and then you're considering the spatial flatness of the three-dimensional subspaces that you're defining by the covector fields.
That seems a reasonable way of understanding spatial flatness as well, but this is flatness like relative to a specific hypersurface.
It seems like it's more general, so you might not have a...
I think the difference with Leibnizian spacetime is that, of course, in Leibnizian spacetime, you're assuming that the spatial metric is flat.
Right, so you could have a generalization of Leibnizian space-time where you've got no connection between where you've just got some three-dimensional geometry for each simultaneity world.
Yeah, exactly. But
And,
I think
and here you've got flatness because it's just one-dimensional, so you don't have a notion of, you don't have enough structure to have non-flatness.
I think the difference is there that you can have those two things come apart, right? If you don't have a flat spatial metric, right, then illusion, in this case, if you don't have a flat spatial metric, then it's not going to be the case that if you try and project everything down, the standard of parallel transport that you're talking about in your quotient space is like sensibly related to your standards of parallel transport in your original space-time.
Even be well defined after quotienting.
No.
Sure, they will be, because if any space-like curve will be sent to a curve, and vice versa, right? So it's only when the curve goes time-like that you're going to have a problem with projecting.
Yeah, but you're going to have to pick a particular projection.
Isn't the unique projection given by the integral curves of psi?
I think this is right, though, because I think this is exactly what you'd expect from that idea that you just articulated.
But we can have this being not zero. We can have
Yes.
cases of spatial non-flatness,
Non-flatness, yeah.
which is different from all of it. Well, maybe not.
Well, so you could just say, I've got some geometry on my space of, one-dimensional lines, and it's Riemannian, but doesn't have to be Euclidean.
Shall we move on and come back to this later?
It seems like a totally reasonable definition. I'm just not sure how it relates to this. I don't know. I'm just repeating myself. Or is it relative to a hypersurface?
I mean, yes, but this holds relative to any space-like hypersurface, right?
Oh, yes, sorry.
So because this holds relative to any space-like hypersurface and any foliation you choose, I would expect that this to be equivalent to the notion that you just articulated, but I haven't proved it.
Okay.
Okay. Which just, there's a picture of what it looks like, right? So you take a space-like hypersurface. If it's flat, then you can take things around that leaf and then get back to the vector you started with. If it's not flat, you don't. Okay. It's kind of interesting to think about the relative strengths of flatness and spatial flatness in our senses. So if you have a Carroll space-time, which is spatially flat, then you can show that, in fact, it's flat simpliciter, if and only if there exists a unit time-like covector field, which is covariantly constant. And the intuition behind this, to get a handle on this result, looks a bit like this. So if you have it that it's spatially flat, right, then parallel transport within any space-like hypersurface of space-like covector fields is going to be path independent. Good. But if it's, in addition, you have a unit time-like covector field, which is covariantly constant, then you can pick your foliation to be the one induced by this unit time-like covector field, right? So then you can get a basis of constant vector fields at each point by, first of all, parallel transporting them along any vector in the foliation. And because it's covariantly constant, they're going to be constant in each direction, right? Because the foliation you've picked has this nice property of being induced by a covariantly constant unit time-like covector field. Does that make sense? Okay. Good. And there's one more kind of curvature condition that you can impose, which is the following. So you can contract, so we already showed, right, if you contract the Riemann tensor with psi in the second index, then the whole thing necessarily vanishes, but it doesn't follow from that it necessarily vanishes if you contract it with psi in one of the other two indices. Okay, so you can ask, well, how should we understand that curvature condition if we chose to impose it? And it turns out that this condition is equivalent to the following two conditions. So first of all, it's equivalent to the claim that the Lie derivative along psi commutes with our covariant derivative. on all tensor fields. It's also equivalent to the claim that there exists a unit time-like vector field whose Lie derivative along psi vanishes, and also the Lie derivative of its covariant derivative along psi vanishes. And if any of the above conditions hold, then this implies that the Lie derivative of the Riemann tensor along psi vanishes. So if you like, when this condition holds, pick any space-like hypersurface you like, fix a value for the Riemann tensor on this space-like hypersurface. That will completely determine the geometry of the entire space-time, because you can recover the Riemann tensor at every point by parallel transporting it along psi. Which is just this idea, right? So if this doesn't hold, then fixing the Riemann tensor on some space-like hypersurface doesn't necessarily fix it everywhere. Whereas if it does, then you have this nice property. And just to kind of think about what that looks like, so we said that it's equivalent to the claim that there exists a unit time-like vector field whose Lie derivative along psi vanishes and the Lie derivative of its covariant derivative vanishes. Well, if you have such a unit time-like vector field, covector field even, then you basically have nice foliations. So you have foliations with nice properties that their curvature, when you parallel transport it up, is the drag of the curvature along psi in the foliation. So you have foliations with constant extrinsic curvature. Does that make sense?
Just add one thing about when this condition is not satisfied. If you go back to the previous slide, this is kind of going to be interesting because this is occasionally a non-trivial evolution for the space-time. The Riemann tensor actually changes, and yet the causal shadow of every event is 0. So it's going to be something that we'll come back to later.
Okay, we spent a lot about like just abstract geometry, so let's actually talk about like physics for a bit now. So Carroll dynamics. We're going to assume that the stress energy content is, as usual, represented by a symmetric upstairs tensor field. The reason it's upstairs is because you ultimately want to get vector field equations out of this, and because raising and lowering indices is a delicate business. If you say that it's upstairs to start with, then you can get a vector field equation by taking the covariant divergence of it. Okay, and the way to think about this is if you pick your favorite unit time-like covector field, then this thing represents the form momentum relative to the space-like hypersurfaces induced by this unit time-like covector field. Okay, and then the dynamical equations are sort of exactly what you'd expect thinking about general relativity, right? So we have this equation on the Ricci tensor, which looks exactly like the trace-reversed Einstein field equations, but we've replaced G with H. And then we have that the stress energy is covariantly divergence-free. Good. So you might know that in relativistic spacetimes and also in non-relativistic spacetimes, so Galilean spacetimes, you have this sort of nice property about the Einstein field equations in terms of the average radial acceleration. You can do something similar in Carroll spacetimes, but it's sort of got some interesting subtleties to it, which is worth drawing attention to. So first of all, the way that the average radial acceleration is usually defined is that you take any three connecting fields. So these are fields whose Lie drag along your vector field vanishes for some geodesic vector field. And you consider the radial components of their acceleration with respect to psi. You can't really do this in a Carroll spacetime because if you let your original geodesic vector field be time-like, then it's just going to be psi up to some constant scalar field, which is not going to give you any new information about the curvature of that space-time. If you let it be space-like, then of course the unit time-like vector field psi is going to be a connecting field, providing that it's suitably well behaved because of the compatibility conditions. But this isn't, again, going to give you information that's not fixed by the compatibility conditions, right? So you need to think about this in a slightly different way. So the way to do it is to, first of all, assume this last curvature condition we talked about, so that the Riemann tensor that you get is fixed by its value on some space-like hypersurface. And then you're going to take a space-like geodesic vector field we're going to assume that it's unit space-like, and then define its average spatial relative acceleration on this hypersurface. And then you can show that the Carroll field equations, which look a bit like the Einstein field equations, are equivalent to the claim that the sort of average spatial relative acceleration, where we're now averaging over two orthogonal directions, so two orthogonal connecting fields, satisfies this property. Is there anything you want to add with this, James? Okay. Good. Yeah, so that's like how you can kind of think about it. I don't. Why is there an opposite arrow there? Okay, there shouldn't be an opposite arrow. But like this is our geodesic, right? Our space-like geodesic, and you have two connecting fields which are orthogonal and also eventually going to be orthogonal to the geodesic. And basically providing the average, if you average along these directions of the acceleration along this, then it's going to satisfy that condition. And finally, we're just going to quickly talk a bit about Carroll energy conditions, because this is helpful for understanding, like, in what sense Carroll spacetimes rule out interesting dynamical evolution. Okay. So, just sort of importing things from general relativity, one thing you might try out is an analog of the strength and dominant energy condition. In general relativity, you might know of this condition because it's useful for proving geodesic theorems. And so the sort of obvious thing you might try in a Carroll spacetime is the following. So you say for any point P in our spacetime and any time-like covector at that point, then we contract it with our stress energy tensor. It's greater than 0. So if you like, the mass or the energy density relative to that foliation is positive. And either the whole thing's 0 or the form momentum relative to that hypersurface, so relative to the foliation induced by our time-like covector mu, is going to be time-like. So time-like momenta and positive energies, which sort of seems fairly reasonable relative to any foliation you choose. Okay, you can show that this actually implies that the stress energy has the following form. So it's the vector field psi, which is our temporal vector field, recall, and then some scalar field which represents the energy density. Okay. And in that case, the Carroll field equations become this. So it's Ricci flat, and you have a continuity equation for the energy density along psi, which is a sort of pretty trivial matter dynamics, i.e. the fluid elements necessarily transverse the integral curves of psi. And the energy density is constant along any such curve, which is pretty boring. It's kind of what you'd expect from the ultra-relativistic limit, right? Because if everything is traveling in sort of causal speed, so you don't have tachyonic matter, then as the speed of light goes to 0, then everything's going to be traveling at the same speed, namely at the speed of light. Okay, good. But you might try and think of some weaker energy conditions which let you have more interesting matter dynamics. So, for example, you might just try and impose that for any foliation you choose, the mass density relative or energy density relative to that foliation is positive. That would be sort of what we're calling the weak Carroll energy condition, which looks a bit like the weak energy condition in general relativity. And this is compatible with non-trivial matter dynamics, but it also allows for stress energy propagation along space-like curves. As a consequence, or perhaps as a precondition. Okay. Good. Shall I keep talking for this section?
Yeah, if you like.
I feel like you've heard a lot of my voice. Okay, I'll keep talking, but you should interject. Okay.
This one's not that long, right? So.
This is quite short. Okay, so we're just going to now talk a bit about the ultra-relativistic limit. So James was saying at the beginning, you can start with your relativistic spacetime. You can do this. You can also do this. What happens if you take a relativistic spacetime and you actually assume that the speed of light becomes very, very small, or that the light cones narrow to become this congruence of curves?
Can I just say one thing, actually? So there is a literature about taking the ultra-relativistic limit already. already, but physicists tend to do it in the way that something like they do for the non-relativistic limit as well, which is, in the non-relativistic case, they consider 1/c expansions, or maybe 1/c squared expansions, and they try and do something similar here, kind of like expand in C, roughly. We're going to do something a little different, a little bit more
geometrical.
A la Malamute 1986, by like actually narrowing the light cones in kind of an analog to how he does in that article. And ultimately what we do is going to be like complementary to the way that physicists do this in terms of expansions.
Yeah, exactly. As you'll see if you look at the proofs. But basically, you know, when you do a limit in a sort of Malmesbury way, you parameterize it by some factor lambda, and then you assume that it has a order 2 expansion and then look at it, which is exactly what physicists do, except they're just setting lambda is equal to c squared explicitly.
Under the hood, they're pretty similar.
Okay, good. So let's just talk a bit about how this limit is defined. So we're going to start with a 1-parameter family of Lorentzian metrics. They're parameterized by this thing lambda, where it sits in an interval between 0 and k. And we're going to assume for the ultra-relativistic limit that it satisfies the following 2 conditions. So first of all, well, actually, let's talk about the second condition first because it's marginally easier. So the upstairs indices Lorentzian metric is going to converge to our temporal metric in this limit for some non-zero vector field, which ultimately we're going to demand satisfies this condition that the Lie derivative along the spatial metric that we get in the limit vanishes. And we're going to demand that if we sort of suitably rescale, right, because we're going to have c squared factors hanging around, so we're going to need to multiply by a factor of c squared to make this whole thing behave mathematically in the limit. And this converges to negative h. The negative sign just comes from the Lorentz signature sign. Okay.
And you need this to make the limit well defined, which is kind of why this is the analog of the closure of the temporal one form in the non-relativistic case.
Yeah.
Where people impose dt is equal to 0 when they're taking the non-relativistic limit.
Yeah.
Sorry, could you get that for free just by considering the fact that the two g and its inverse, the inverse relationship up to a factor lambda, and you're setting lambda to 0.
I mean, when I did this, it doesn't drop out like that from the mathematics.
Okay.
I mean, perhaps there is a more sophisticated argument. For what it's worth, when physicists do this, they also think that you need to impose this as an initial condition. They're sort of interested in taking non-regular limits when you don't impose this. But basically what happens is you end up with a term in inverse powers of 1 over lambda, and you need to show that, that this term actually vanishes for the whole thing to converge. That looks like the Lie derivative of h long psi. Does that help?
The thought was just that the Lie derivative of HAB will be some combination of contractions of psi with HAB and things you do with nabla. But those compatibility conditions are going to be preserved in the limit anyway. So assuming those, it comes down to whether psi and h are compatible. You'd have thought that compatibility you get for free in the limit.
Yeah, no, but the issue is that you're not guaranteed convergence to any derivative operator in the limit until you impose this. So it's true that if it converges to some derivative operator, then that derivative operator will be compatible. And so as a result, you would get this for free. But there's no nothing to ensure that it converges to any derivative operator at all in the limit, unless you impose this to start off with. Okay. Yeah, and again, this just sort of corresponds. So lambda effectively corresponds to c squared, which is a bit like what physicists do when they do a c squared parameterization, and changing it so it goes to 0 then sort of amounts to taking the night codes to narrow till they become congruous of curves, i.e. the integral curves of the vector field psi. Okay, good. So there are sort of 2 interesting propositions. The first proposition is that providing these conditions hold, then the family of associated connections for this one parameter family of metrics will converge to a Carrollian connection. So you sort of can break this up into two parts, right? First of all, they converge to some derivative operator in the limit that lambda goes to 0, and secondly, this derivative operator is going to be compatible with psi and h in the limit. So it's a Carroll spacetime. Good. And you might also be interested in the second result about what happens to the dynamics in the limit, right? So we need to say a little bit more about how the stress energy tensor behaves in the limit before we can show something to that effect. So we're going to now suppose that for every lambda we have a symmetric stress energy tensor T, and we're going to suppose that for each such value of T, Einstein's equation holds with respect to the relevant connections and their associated Ricci tensors, and we're going to assume that it converges with these powers in the upstairs indices T. The reason that we're assuming convergence here is, again, because we want to show that you can get out a tensor that you can use to write down vector field equations, which is, again, useful if you want to have dynamics, right? Okay, good. And then we have another nice proposition, which is exactly what you'd like it to say. So if you now supplement your structure with T, so for each value of your Lorentzian metric, you have an associated value of your stress energy tensor, and these all converge in the way that we said that they do, the limit, then first of all, there exists a symmetric tensor field which it converges to. Also, that the scalar stress energy converges to some scalar field here. And moreover, in the limit, these satisfy the following two conditions, which recall were exactly the conditions that we said were the dynamics of Carroll gravity. So you really do kind of get the dynamics of Carroll gravity out in this light cone narrowing limit. Okay.
Should we skip this?
Yeah, let's skip frame theory.
Yeah.
Do you want to talk about?
Yeah. Shall I carry on now?
Yeah, go.
So just to say what we're skipping, so there's a way of kind of making more rigorous, taking the non-relativistic limit, which is to think about the models of frame theory, which is some unified theory, which in some sense incorporates the models of general relativity and the models of non-relativistic gravity. The point that we're making in the slides that we skipped is it also incorporates the models of ultra-relativistic spacetimes. And so insofar as someone is doing something like Ehlers or later Sam does of trying to think about the non-relativistic limit rigorously by putting a topology on the space of models of frame theory and thinking in that way, you can do the same thing with the ultra-relativistic limit.
Yeah, and like also interestingly, some people sometimes claim that frame theory's models are just the union of the models of general relativity and Newton-Cartan theory, which is clearly false in light of this, because they also, by definition, include the models of Carroll gravity as well.
All right, so thanks for all of the details of Carroll gravity. Let's think a little bit about why people might be interested in Carroll gravity. So when we were looking at the literature, we could isolate three main motivations which people give. So to better understand asymptotics, and this is the thing that you'll find most often in the recent physics writing on Carroll gravity. Second, because it seems to be the correct space-time setting for ultra-relativistic physics. And third, which I think is the most attractive option, to explore the space of space-time theories. So I will go through all of these. So let's start off with asymptotics. So just to remind you, the Bondi-Mesner-Sachs or BMS group is the asymptotic symmetry group of asymptotically flat Lorentzian spacetimes at null infinity. And it was surprising for people when they were studying this to start off with that the BMS symmetries include not only the Poincare transformations, but another infinity of symmetries known as the BMS supertranslations. So there's a sense in which, at least not straightforwardly, you're getting special relativity in the case of weak fields at long distances in general relativity. Actually, things are a little bit more complicated. And physicists have spent a lot of time studying the BMS group. We would like to understand better the geometry of null infinity. What Duval and Horvath and Gibbons realized in 2014 is that the BMS group is the conformal extension of the Carroll group. So if you include conformal transformations alongside your Carroll transformations, you actually get the BMS group, which is kind of cool and interesting. So the thought then is that Carrollian structures might offer an attractive way of understanding the structure of null infinity. And somewhat relatedly, so two things. So this is related also to what sometimes people call flat space holography. So in holography, if you think about like ADS CFT correspondence, we're often interested in the case in which spacetimes are asymptotically ADS. You might be interested in the case of trying to do something with holography where the spacetimes are asymptotically flat, so flat space holography, and again, Carroll's going to come up in that literature as well. So anything to do with asymptotics, to do with this kind of holography is probably going to have Carroll in it somewhere. Like I said, somewhat related to this is the fact that in a sense which Duval and Horvath and Gibbons explain the geometry of light cones, it just is Carrollian. What we mean by this is thinking about what's known as null reduction. So sometimes people think about the non-relativistic limit in terms of null reduction. What you do is you take a certain 5-dimensional general relativistic solution and you project onto the null directions. You actually get Newton-Cartan spacetimes out. You can do something similar in other 5-dimensional relativistic spacetimes and project onto the null directions, and you'll get the Carroll spacetime out, which is kind of also quite cool. Okay, so that's one motivation anyway. Just set that aside if you're not interested in it. Like asymptotics and holography is one reason why people care about Carroll gravity. The next thing to say was, and this is slightly more philosophical, it seems to be the correct spacetime setting for ultra-relativistic physics. So how to understand this? Well, you might say something like this. Physicists do from time to time have occasion to take the ultra-relativistic limit. As one example, which I remember from my undergrad, consider ultra-relativistic gases as discussed in chapter 25 of Blundell and Blundell. But also high-energy particle physics, synchrotron radiation, cosmic rays, jets, and astrophysics, etc. These are places where you'll find physicists talking about ultra-relativistic limits. It doesn't seem unreasonable to claim that the right spacetime setting for those, the right spacetime geometry in those cases is Carrollian, at least if you're thinking about things in a certain way. So one way in which you might think about this probably requires more like philosophical exploration, but it seems right, is if you take the Carroll spacetime to be a stand-in for the environment or for the other particles when you're considering some particle which is moving ultra-relativistically, then there's a sense of it, yeah, the Carroll spacetime is modeling all of the other stuff that's going on when you're looking at something which is moving at very high velocities. It's in that sense that Carroll spacetime looks like a good tool to use when you're thinking about ultra-relativistic physics. The third thing, which like I say I think is the coolest, is to explore the space of spacetime theories. So here we have good old Dennis and Schumann and Scholz. This is a great volume called Towards the Theory of Spacetime Theories, where the editors are inviting philosophers to look not just at general relativity, but to a richer space of spacetime theories and see how various features of general relativity, like the equivalence principle, etc., might carry over to the broader context with the hope of understanding those principles better. This has actually quite a long precedent. So the title of that book is an homage to this paper by Thorne and Lee and Lightman called Foundations for a Theory of Gravitation Theories. I think that not enough philosophers know about this. It's a really amazing paper which discusses many interesting features of Newton-Cartan theory in a way which reads like it was written like 2 years ago. So if you haven't read it, I would strongly recommend having a look. But you can slot Carroll gravity into this kind of framework. So here's another paper by Lévy-Leblond, but also his co-author Bakri, called Possible Kinematics. And I think this is something which also deserves further philosophical attention. What these authors are basically doing is considering something like a Lie algebra version of Ignatowski. So they're insisting that you have boosts, they're insisting that you have spatial homogeneity, and they're insisting that you have rotations. And what they show is that there are 11 possible kinematical algebras compatible with those demands. Somewhat like a Lie algebra version of the Ignatowski transformation. I think this is like cool and interesting. We should look at it more. I'll say a little bit more about it, but just as a discussion of what physicists have done with this since 1968 when that paper was written. So Huang et al. Have explored all of the space-time structures associated with each of those algebras. Bakri and Lévy-Leblond's work was extended to all space-time dimensions and set in the context of another thing that we like, Klein geometries, by Figuera, O'Farrell, and collaborators in 2022. Morand, who's an amazing mathematical physicist, considered all possible ambient kinematics, which means all possible extensions of those 11 kinematical algebras by scalar ideals. It turns out that there's a lot of stuff there. All of which is to say, I think there's a lot of like interesting stuff to look at here. But let's just hone in on the theorem from Bakri and Lévy-Leblond, because this is easy to understand. So under the assumptions that space is isotropic, parity and time reversals are automorphisms of the kinematical groups, inertial transformations in any given direction form a non-compact subgroup, then there are 8 types of Lie algebras for kinematical groups corresponding to 11 possible kinematics, which are these things. And some of these things are familiar, like the Galilean Lie algebra or the Poincare Lie algebra. But other things are far less familiar, like the para-Poincare algebra or the para-Galilei algebra. Notice also you get de Sitter algebras out. And also Carroll lives there right in the middle. So if I want to be exploring like all possible kinematical structures for space and time, it seems like a good idea to look at theorems like this. And there's a lot of things, including Carroll gravity, which philosophers have just not looked at yet. There's some nice figures in that paper. So they write down all of the algebras for all of the 11 cases here, which is quite a nice resource. If you're interested in the kinds of things that Morand does, it gets a little bit more intimidating. So these are all of the possible algebras with extensions by scalar ideals. So I would have thought the Bargman algebra is there somewhere, but I can't find it.
Oh.
You might name it something else. Anyway, it's just to say that there's even more stuff to look at.
It's essentially extended Galilei.
Yeah, okay, cool. So it's here.
AK3.
Nice. Okay, so those would be the 3 kind of motivations that you might have from physics to look at these things. I guess the third is kind of philosophy adjacent. Good, we have a bit of time to come back to some properties of gravity now. So now we can bring to bear some of the things that Eleanor was talking about to try and sort out some confusions that you'll find in the literature about Carroll gravity. So recall from Lévy-Leblond's quote that I gave at the start, the following 2 properties of Carroll gravity. First, an attenuated notion of causality in the sense that almost every pair of events is space-like separated. And second, a lack of absolute temporal distance between spatially separated events. So interpreted literally, Carroll spacetimes are strange. Every body is causally isolated from every other one, despite their standing in absolute spatial relations to one another. Over coffee, Oliver said, this is kind of Leibnizian. I can't spell Leibniz. But sort of like monads, right? But here's a puzzle about motion, which you'll find on regards the first of these points, which you'll find in the physics literature on this. So there seems to be a tension between what different people are saying. So on the one hand, you have Hansen and collaborators saying this: particles with non-zero energy cannot move in space anymore. And for these particles, there can be no interactions between spatially separated events. But that seems to be resisted by other physicists who write on this, like Berkhoff et al., who argue that while it's true that a single free particle in Carroll spacetime can't move, that's not true for multi-particle systems, where they write only the center of mass can't move, but the separate particles have non-trivial dynamics. To lowest order, the velocity of the center of mass is conserved, which implies non-trivial dynamics for the separate particles. So how am I to reconcile things like this? Well, one way to do it might be to appeal to the different kinds of Carrollian energy conditions which we were talking about before. So if you assume that the stress energy propagation is time-like at the outset, then it's indeed the case that matter dynamics in Carroll spacetimes become trivial. This is what Eleanor was talking about with the strength and dominant Carrollian energy condition. Carroll gravity is consistent with non-trivial dynamics of matter if you allow stress energy to propagate along space-like as well as time-like curves. So in the first case, you're adopting something like, as we said, the strength and dominant Carrollian energy condition. There can be no space-like propagation of stress energy content. But if you invoke only a weaker Carroll energy condition, like the weak Carroll energy condition, then there can be space-like propagation. And it seems like this is one way of offering some kind of rapprochement between, I'm using gym words, between those two people. Because certainly one of these 2 sets of papers has a stronger idea of what kind of interaction between our Carrollian bodies is possible than the other one does. You also find people worrying about the lack of absolute temporal standard in Carroll gravity. Again, I think this is an area where we philosophers can contribute something. So the lack of an absolute time standard in Carroll spacetimes might strike you as puzzling, but maybe less so when you remember that it's not something you have in general relativity anyway. The lack of an absolute time standard is not regarded as a problem in relativistic physics as long as you can build and operationalize suitable clocks in relativistic spacetimes. And the thought would go, well, you need to investigate whether that is possible in Carroll gravity. Although you might think that the structure of spacetime is going to make this harder. What do extended bodies look like in Carroll gravity? It's how do I make a Langevin clock in Carroll gravity more clear?
So by absolute time, you mean, I presume, time shared between different locations, not there being a temporal metric on the integral curves, because presumably there is a unique metric on the integral curves.
Yeah,
just
fair.
integrate any unit time. Like
Yeah, fair. But still, I think challenges with how you'd actually like operationalize time in Carroll gravity.
You could operationalize time at a point, right?
Sure, yeah.
But you couldn't. It's not clear how you'd operationalize a notion of time between different non-co-spatial points.
So I spread time through space when I can't.
As it were, a unique temporal metric for each monad. It's just
Yeah. So they all have like an
Yeah.
internal clock, if you like, and in fact having to sort of, in a weird sense, agree on this. But
We have 4 minutes for the last section. Shall I give it a go?
yeah, let's go for it.
Okay, so future prospects. So you might be interested in thinking about whether my curved spacetime Carrollian theory is equivalent to a flat spacetime potential-based version of Carroll gravity, just like Newton-Cartan theory. The curved spacetime non-relativistic theory of gravity turns out to be equivalent via the Troutman geometrization and recovery theorems to the flat spacetime potential-based version of Newtonian gravity, which is itself known as Newtonian gravity. There are promising signs that the answer is yes here. You might also be interested in doing what Eleanor and Will and Quentin Vigneron and I did of looking at ultra-relativistic limit of the geometric trinity of gravity, which I haven't explained yet, but rather than the non-relativistic limit. You might also be interested in thinking about how Weyl tensors and conformal structures behave in the ultra-relativistic limit, and you might, getting more niche now, be interested in Carrollian constructive axiomatics. Okay, so let's start off with Carrollian recovery. So it would be nice to show that curved spacetime Carroll gravity is equivalent to a flat spacetime potential-based version of the theory, i.e. prove some ultra-relativistic version of the Troutman recovery theorem. Another way to go, which is the kind of thing that Quentin does, is to do a 3+1 projection. So Quentin projecting the Newton-Cartan structures onto space-like hypersurfaces kind of derives something which looks like the Newton-Poisson equation. So could we do something like this? Actually, before we... Did you want to say something?
Are you going to talk about the
Kind of already did this.
potentials issue?
Maybe we can leave it till the...
We can leave it to the Q&A. Yeah, sure.
Yeah. We were thinking about this, and then we called Quentin, and he'd kind of already done it. So there's evidence that this is indeed possible. But this is a different way of approaching the relation between a flat space-time theory and a curved space-time theory than Troutman geometrization and recovery, or at least people haven't explored the links between these things much. So in terms of the ultra-relativistic trinity, so Will and Quentin and I show that there's a non-relativistic version of the geometric trinity of gravity, which, just to remind you, is the fact that you can reformulate general relativity in terms of space-time torsion or space-time non-metricity instead of space-time curvature and get theories which are nevertheless dynamically equivalent. We do this by writing the GR field equations in terms of torsion or non-metricity and then taking the non-relativistic limit. You might ask, can I do this analogously with the ultra-relativistic limit? We kind of started doing this, but we're not done yet. And when you have done that, you might also start being interested in the common structure, just like Will and Eleanor and I did in this article. So this is all stuff to be done, but we're making a stab at it. In terms of conformal structures, there's some interesting stuff here. So I don't think everyone knows that in general relativity, there are two different Weyl tensors. There's the conformal Weyl tensor, which we know and love, but there's also what's known as the projective Weyl tensor. So this is an invariant under conformal transformations, and this is an invariant under projective transformations. And provably, these are equivalent in general relativity. So we have this theorem that for a given connection on a four-dimensional manifold, the projective and conformal Weyl tensors associated with this derivative operator only agree if this is the Levi-Civita connection of a metric which satisfies the field equations. When you take the non-relativistic limit of the Weyl tensor, which is something which Ehlers and Booker did, but also Neil and Jim did in this 2018 article, curiously, you find just this guy. Neither of these sets of authors recognize this as the projective Weyl tensor, but so be it. But there's a good explanation here, which is that when you take the non-relativistic limit of conformal structure, it actually becomes kind of delicate and in some sense degenerate. So it's kind of no surprise that you're just left with the projective invariant. But all of this raises the question, what would happen to my Weyl tensors if I took the ultra-relativistic limit? Eleanor and I had a go. but it doesn't look like good stuff happens. So if you take the ultra-relativistic limit of the file tensor by doing the kinds of things that Eleanor was doing in the section on the ultra-relativistic limit, actually just get objects which are divergent. You might also try to follow the strategy of Neil and Jim of trying to construct some object which has the right properties, the right symmetries, i.e. the symmetries of the Riemann tensor being trace-free, etc. But you don't get anything nice by doing that. I think we're kind of pessimistic. Yeah. So
part of the problem is that there isn't a well-defined Ricci scalar in Carroll gravity. So you're lacking certain identities which you use to cancel terms when you take a trace, which is the problem.
So this seems like an interesting disanalogy. Like I have these two projective and conformal Weyl tensors in general relativity, and when I take the non-relativistic limit, one of them kind of fizzles out, but I'm left with the projective Weyl tensor. When I take the ultra-relativistic limit, I just don't get anything good, worthy of further thought. Nevertheless, there's another plausible notion of ultra-relativistic conformal structure, roughly absolute spatial angles between temporally separated events. Conjecture, you could use something like this to prove something like Weyl proved in 1921. This has to be in the talk by me, right? Projective and conformal structures plus other stuff, space-time structure, or even do ultra-relativistic constructive axiomatics, but a task for another day, I expect. So, just to summarize, we've introduced Carroll gravity and its geometrical structure. We've motivated its physical interest. And we've presented a bunch of things which we regard as being interesting projects for the future. So thank you.
Great, thank you both very much.